we've learned all the major assumptions. Like I told you guys in the last class, they are not the only assumptions. They are not the only assumptions. They are just the major assumptions. So what we are going to learn today is regression analysis. Linear, when we talk about regression, regression can be linear. We have different types of regression. So we're going to talk about the ordinary least square regression. So that's what we are going to focus on. So under the ordinary least square regression, we have two types. We have the simple linear regression and we have the multiple linear regression. Now, what's the difference? First, let me start by explaining what we mean by regression and when do we use it. Like I've been saying, you are a doctor, data doctor. People come with their problem. They tell you their problem. So you'll be the one to recommend the best method to solve that problem. So you are a data doctor. So for you to recommend the best method, you need to know different methods, have them handy, and also know when to use them, know what they are used for. That's how you become a data analyst. So what regression? Regression talks about the relationship between variables, the relationship between a dependent variable. We are talking about any definition I'm giving now is majorly for ordinary least square regression. So we are talking about the relationship between a dependent variable and one or more independent variables. We are talking about the relationship between a dependent variable and one or more independent variables. Let me explain. Okay. So when we talk about regression, we're trying to see if I know B and C, is it possible that I can use B and C to predict A? If I know, let me use football match. If I know what man you played in the last match, what they played in the, 2 matches ago, the last 2 matches and the last match, if I know what they played in their last 2 matches, is it possible for me to predict what they will play today? So that's what we're talking about in regression, the relationship. You know the independent variables. You want to use the independent variables to predict, to estimate the dependent variable. So now for you to understand regression very well, you need to know that we have independent variable and we have dependent variable. So we are using the independent variables to predict the dependent variable. I'm not teaching regression now. I'm just showing you how to do it using SPSS and Minitab. So if you want to learn more about regression, you can go online and learn more about regression. But just know basically regression is about relationship. So if I want to know if my grades, my score in an exam, if it depends on the number of hours I spend reading, that's the regression analysis. So that means if I know the number of hours a student spends reading a course, I should be able to tell the student the score they will get in that particular course. So if that thing is, if it's possible, if there's a relationship, we talk about regression. So for you to do a regression analysis, first you have to test for all the assumptions, all the assumptions. So you test for all the assumptions of the regression analysis. So let's start. We've been doing it. So if you want to do regression, you go to analyze regression and you go to linear. Okay, no, let me use another data. Analysis, regression. Let me use, no. Let me use, I think this is the assignment I gave to you guys. So we are using GDP as independent variable. So we'll go to analyze regression linear. Analyze regression linear. You click your dependent variable, you move GDP. Independent variable, you move inflation, you move population, and you move USD. You go to statistics, you click multicollinearity, you click Durbin-Watson for autocorrelation. You can click descriptive statistics just for you to get a summary of your data Okay. You go to plot, you plot the residual versus predicted. That's for constant variance, also called homoscedasticity, also called no heteroscedasticity. You click normal probability plot. So someone did an assignment and I was trying to correct the person. The person was doing normality test for all the variables. You don't need to do that. So just come to this normal probability plot. Do the normal probability test for the errors. That's what this thing is doing. You are not doing for each of the variables. You are doing for the errors of the model. So you don't need to save. Another way to do it, you can save the errors and do the normality test. So this is how to do it manually. If you want to do it yourself, go to save and save the error. On standardize, you save it. Then after saving the error, let me just see, I'll come back to this. After saving the error will save. What happened? Look at the error. After saving the error, then you go to probability descriptive PP plot and do the normal probability test yourself. So this is how to do it yourself. Don't go and do normal probability plot for all the variables. Do for the error term. But SPSS already gave us the option to, once you tick it, SPSS will do the normal probability test for you. So you don't need to do save and do it yourself. Like save and start doing it yourself. So if you want to use Malanobis distance to test for outlier, this is where to click it. Remember I told you Malanobis distance can be used to test for outliers. Now, the difference between Malanobis distance and the other methods, if you want to use the other methods to test for outlier, you have to start testing each of the variables if there is an outlier. But if you are using Malanobis distance to test for outlier, Malanobis distance will consider the cases, not necessarily the variable, the cases. So it will consider it generally and tell you the cases that have outliers. When I talk about cases, so let me go back so you understand what I mean by cases. So this is what I've done. I will still go back. So this is the Malanobis distance. So it will tell us the case that is it case 1 or is it case 12 that has an outlier. It will just tell you that case 12 has an outlier, but it won't tell you where the outlier is coming from. Is it from inflation? Is it from USD? Is it from GDP? Is it from population? It will not really specify it. It will just point out that case 14, there's an outlier in case 14. So that's the difference. But if you are using box plots or the graph test, or you test for each of the variables and it will tell you the particular case that has the outlier. So it's like maybe I will not use, don't know yet. Okay, so let me return back to what I've been doing. So I can delete this, and go back. So I've been trying to explain. So let me go back to my, okay, so analyze, regression, linear. So we don't need to save the residual because we can plot it directly. So there's nothing again here. Okay, option, there's nothing here. So I'm done. So I can click OK. So the next thing. Now, this SPSS use the correlation and this to test, and VIF to test for multiple linearity, but I will not use correlation. I will not use this. I will just use I prefer using VIF. I will use VIF. So let me copy all my results. So let me delete this first. I'm not using it. I delete this. Also, this WAP condition index, which I also try to explain, they use it to test for the WAP condition number. So I'm not using this. Then for this, the Malanobis distance, look at it here. So I will delete the rest and leave only Malanobis distance. As if I want to use Malanobis distance to test for outlier. So I can copy my results now. When you want to copy your results, you hold Control and click all the things you want to copy. Just hold your Control. as well. Then you still holding your control, you press C, that is control C, copy. So that's all. Then you move to Word. Then you paste. So that's it. So you paste your results. Then you start to interpret. Then you can also arrange your table the way you want it. Like I told you, I don't like keeping my table this way, your choice. So you arrange your table the way you want it. You must not follow me. Do it the way you want it. Now for this, okay, this I may not report it, so I may delete some things. Now the result comes out with both unstandardized and standardized. So normally I like deleting the standardized because I don't use it. I don't report it, so I delete it. I normally delete it. So I can copy this and replace that. Both um, I'm trying to avoid explaining some things because they are not really necessary. Yes. So what we interpret is only the unstandardized. Now the standardized, some people may decide to use it or not. But what we are interpreting for this class is the unstandardized. So I've already copied this. So I want to get a table that will have only the VIF. So after copying it, I'll go back to this, double click this, and delete the rest. I will delete all these. Maybe I can delete. Let me see if I delete this, it may, okay, correct. I just want VIF. Where is it? Okay. So I can paste it. Remember, you're supposed to do the assumptions first before you do any other thing. So this is the first assumption. This is the assumption, Dublin Watson. So I'll move these two up because I'm supposed to test for the assumption first. So I'll cut. My system is slow. Cut. You can start with any of the assumptions you want. So now I'm starting with multicollinearity, normality, constant variance. Okay. Yes, I've seen. I'm coming. Now, okay, we can't continue with this analysis. Like this analysis failed the autocorrelation assumption, so we can't continue. So if once an assumption is not satisfied, you can't continue. I think it failed based on the assignment they did. It failed the W. Watson assumption, so you can't continue. Then before Oyemachi will ask his question, let me explain something. Now, for this normality plot, someone may look at it and say it's not normally distributed. Another person may look at it and say it's normally distributed. Now, to know if we are correct, I will move my data from this to Minitab. GDP is the third one. I'll move it from this to Minitab. Or I can just repeat the analysis in SPSS and save the error term. Or repeat the analysis in SPSS, then save the error term. I can remove my nodes now, save only the error term, unstandardized. Then I move the error term. I move the error term to Minitab. I can call it residual. So I plot the error term. So I go to start, basic statistic, normality test. This is just to confirm using p-value. That's what I'm trying to do. So the same plots. So look at the p-value. I think it should be the same plot. Okay, this one, okay, yeah, this plot use the standardized. So it still should give you the same result. Yeah, I use the standardized, we're using the unstandardized. So which is also correct. So let me use the unstandardized. So let me save the unstandardized. Let me save the standardized and remove the unstandardized. So I just save the standardized, so I can move the standardized to, I can move it to Minitab and test. Add normality. Okay. I think the two plots should be the same. Okay, they are the same thing. And they should give you the same p-value. This one is the standardized, this is the unstandardized. For Minitab, give us the same thing. So using the p-value shows that 0.437. The null hypothesis is that it's normally distributed. Alternative is that it's not normally distributed. So because the p-value is greater than our level of significance, we are not going to reject. As we are not rejecting, it means we are going with the conclusion that the errors of the model follows a normal distribution. The errors of the model follows a normal distribution. So the normality assumption here is satisfied. So based on the assignment I gave to you guys, the Durbin-Watson assumption is not satisfied. So look at it, it's very small, it's less than the DL. So because it's less than DL, it's not satisfied. So what do? You can't continue with this analysis. You can't continue with this analysis. So you have to look for another method that you can use to do the regression. Maybe you consider what we call principal component regression. You consider rich regression. You can now consider machine learning. You just consider other ways to do your regression, but you don't. What we are using now is ordinary least square regression. So since the assumption of the ordinary least square regression, they are not satisfied, you can't continue using them. So you now look for another type of regression to use or look for a way to solve the problem. So Yemashi, you can ask your question. Why I look for another data we can use.
No question, I'm not understanding.
You are not understanding.
Yes.
You can't. You know why? Do you know why you're not understanding?
No.
It's because have you gone through the last video?
No.
That's why you cannot understand. You cannot understand.
It's revision.
Eh?
I did revision.
No, I've explained all these things in the last video.
Okay.
I've explained what we mean by assumptions. Like I've explained this, I've explained this. And so if you go through it, you understand it. I've explained this.
Okay.
Let me even show you to, and people understood it. Let me show you something. So if you go through the last video, you will understand it. Let me show you. Even the assignment I received, I'm coming. Or let me use my WhatsApp. A minute. So, Emmanuel, that's why it's good to go through the last video before the next class, because I will assume that you have gone through the last video, class, and I won't be explaining all those things again. You get?
Yes.
So you always go through the last class before the next class. So all these things have been explained in the last video. Okay. So I just want to show you guys what someone did. I want to send it. No, let me not send it to the group. I want to show you guys what someone did. Okay. So let me open it. OCP. No. SPSS Minitab. Assignment. This from OG and OG and Imo. Both of them have been serious. They work together and they've been very serious. I'm proud of them. So look at what they did. I don't know why my system is slow today. Okay, look at what they did. I see. They tested for autocorrelation, yeah. The same thing we did. They got the same thing I got now. So they rejected the null hypothesis because this is less than. So when you go to the last video, you know why they rejected. It was explained. They also tested for multicollinearity using VIF. I see they did what I just did. They tested for normality. Now they didn't take their result to Minitab to get p-value, which is also okay. They tested for homoscedasticity. Then they tested for outlier using box plot. So if you want to test using box plot, it was also explained. So now what I wanted to use here is a Mahalanobis distance. So you can also test using box plot or growth test. So let me look for another data that will satisfy the assumption. So this data didn't satisfy the assumption. So whenever the assumption is not satisfied, you don't continue. Let me use Kelechi's. No. Okay. So let's use this. So repeat the same analysis. Analyze regression, linear. Cap will go to dependent variable. So Emmanuel, what I'm teaching today is I want to teach regression, but the explanation of the assumptions are from our previous class. So when I want to start explaining anything new, will be from the interpretation of regression analysis. So far, I've not even done anything new. What I'll be doing now is a revision of what we did in our last class. Do you understand? But I'm not explaining in details. They said GDP is our dependent variable. CAP is our independent. REC is our independent. So you go to statistics, you save descriptive, you save collinearity, you save Durbin Watson, you click continue. You go to plot, you plot residual versus predicted. Then you click normality plot, continue. You go to save, maybe let's see, you can save Mahalanobis distance, continue. Then you click OK. So this is it. So the result started here. The result started here. So let's see who can interpret it now. So you copy you copy all your results. So when you copy your result, this is what you have. So you copy your descriptive statistic. We've learned that we interpret the mean and the standard deviation. Now, if you want to interpret standard deviation, on that way of interpreting it, instead of you saying the standard deviation is 39006, you can say the deviation of the uh, data from the deviation of for how will I put it? The deviation over the years for GDP. Okay, the deviation from the mean over the years for GDP is this. That's how to put it. Then the deviation over the deviation from mean over the years for CAP is this. The deviation from mean over the years for REC is this. So that's another way of interpreting standard deviation. Let me say it again. The deviation from mean for GDP is this. The deviation from mean for CAP is this. The deviation from mean for REC is this. So you can, that's how to interpret it instead of saying standard deviation. Mean is also interpreted as average. So you interpret your descriptive statistics. The next thing is you test for if this is not compulsory. I was just looking for, because the guy said he wanted more pages. So I now had to give him a line plot. I've taught this already, how to get a line plot. So if I want to get a line plot, this is not really compulsory for regression analysis. If the guy wanted more things to be added to his work, so you just go to graph chart builder and go to line plot, which I've taught already. Remove this. So you want to get line plot for what? CAP. Let me see. So this is the line plot for CAP. No. You put it the other way. Reset. Line plot. Year will be here. Y rec will be here. So something like this. So this is what I did. So are you seeing it? So it's not that it's compulsory. Like when you want to do analysis, it depends on what you want. Nobody will force you. So he said he wanted this. I didn't explain anything for him here. I just gave him the plot. So now if you want to explain this yourself, you can then, you may not really explain, just say the data is shown graphically using the line plot. And the graph shows that there is an upward trend. That's maybe the little interpretation you can give. There is an upward trend. The highest, I think, was recorded in 2019. It was an upward trend with the lowest in 2004 and the highest in 2019. So look at it, 2019, 2004. It was an upward trend. You also interpret for REC, it was an upward trend. You can say it moved from this place to this place. Then it experienced a little drawback before it continued moving up. So you can, that's how you interpret it. It moved from 2004 to 2010. Then between 2010 and 2012, it experienced a little drawback or a little setback. Then before it started moving upward again. But this is an upward trend. They also interpret this that it had both and how will I interpret this? You can just say from 2004 to 2004 to 2008, yeah, maybe 2008 or 2009, it was they experienced a steady increase. Then between 2009 to 2016, there was both an upward and downward fluctuation. So you say from 2004 to 2009, it experienced a steady, the keyword there is steady upward increase. Then between 2009 to 2016, there was a upward and downward fluctuation. Then after 2016, it experienced an upward trend, a steady upward trend. So, like I said, this is not really important. It's just if you want. And because it wasn't part of what I wanted to do for him, I didn't spend time interpreting it. I gave it to my client to interpret it himself. So you have to do a good job for your clients So you always have to interpret your work. So this is where the main work started from. So whenever you want to do any analysis, you test for the assumptions, which I explained in the last class. So now the first assumption we are testing is autocorrelation. What's the autocorrelation value? Like I told you, you can write your work like this, or you can just write it like a sentence. If I want to write it like a sentence, I would say the assumptions of the OLS, I mean ordinary least square regression. Always specify and state that it is ordinary least square regression, because like I said, we have different types of regression. We have principal component regression. We have ridge regression. We have partial least square regression. So we have different types of regression. Always state that what you are doing is ordinary least square regression. So the assumptions of the ordinary least square model are tested to determine if the data is stable for the OLS method. So you can also continue writing. 4 assumptions will be tested in this work or in this research or in this study, namely autocorrelation, multicollinearity, outlier, and the rest. Full stop. Then you start the first one. The result, you can also continue. The result of the test for the assumption are given below. Then the first one, test for autocorrelation. Instead of you writing it the way it is here, H0 and H1, you can write it in words like I've been saying. You can just say the autocorrelation assumption was tested at 0.01 level of significance, full stop. The null hypothesis for the test is that the residuals are not serially correlated, and this was tested against the alternative hypothesis that states that the residuals are serially correlated. I'm writing it like a sentence. If you watch what I just did now, I just stated the null, alternative, and the level of significance using writing it in words without stating it this way. Both of them are correct depending on what you want. Then full stop. I'm continuing my interpretation in words. The Dublin-Watson statistic for the test is this, and the decision rule, you state this, will aid me to know when to reject and when not to reject my null hypothesis. Then this and this are gotten from the table. So Onyema Manuel, this was explained in last class. So you get this and this from the table. So when do you reject? You reject when this value, if this value is less than this, you reject. When do not reject? You do not reject when this is greater than this. And in this case, it is greater than this, so we are not rejecting. So since we are not rejecting, it means we are going with this, that the residuals are not serially correlated. That means our data passed the first test. Our data passed the first test. Now, what we mean, test of assumption means there are conditions that the data must satisfy before you can use the OLS model. So if the data doesn't satisfy the conditions of the OLS arrow model, we can't use the OLS arrow. Then we have to think of using maybe the principal component regression or any other method. So we have to always confirm that the data will pass all the assumptions. So like I said in the last class, if the data fails one assumption, you don't continue. It must pass everything, just like your WAEC. If you fail mathematics, you can't continue. Even if you got A1 in the other subject, you can't continue. So that's how it is with assumptions. So that's why if you watch what we are working with a different data, we had to stop. Why? Because that data failed the autocorrelation assumption. So we could not continue, we had to stop. Test for multicollinearity. You test for multicollinearity. So look at, I did the analysis now. This is what we got for test for multicollinearity. You see the VIF. Look at the VIF here. Look at the VIF here. So you will say there's multicollinearity when the VIF is greater than 10. So these VIF, they are not greater than 10. So you also mark this. It has passed the test. It has passed the test. You know how to interpret this. You then go for outlier. So for outlier, let me see if I can use a box plot for this. Graph, that method, you go to box plot, reset, remove this. Okay, plot. This one told us that there's an outlier in 16. GDP. no outlier. Reg, no outlier. So CAP told us there's an outlier in case 16. So let's go back to our data. Case 16, there's an outlier. That's for which variable? That's for CAP. So there's an outlier for CAP in case 16. CAP case 16. So this is an outlier. That's what he's trying to tell us. So let's see. Let me take this data to Minitab and use the other method, the grubs method, and see if it will see anyone as outlier. So if you want to do the same thing in Minitab, so what I clicked Control N to start afresh. So that's what I clicked. So let me see. GDP, rec, and cap. GDP, GDP, rec, cap. So let's do the same analysis here and use another method to test for regression. Are we seeing it? So you go to start regression, and you go to fit regression model. You move your GDP to as response, rec, and cap. Then you go to option. Everything is okay here. Graph. You click your normal probability plot. Look at the residual versus fit. This is the one for constant variance or almost skedasticity or no heteroskedasticity. That's the residual versus fit. You know, in SPSS, you have to be the one to tell SPSS what and what to plot. But in Minitab, you just tick the box. So results, you click your W1 thing. Storage, we don't need to store anything. So I think we can go. So this is the normal regression. So now let's test for outlier. Outlier test. So I move GDP. Okay. There is no outlier. P-value is greater than 0.05. It agrees with the box plot. Let me go to rec. There is no outlier. It's greater than 0.05. It also agrees with the box plot. So let me try cap. Cap in box plot said there's an outlier. Are you seeing it? It also has, are you seeing this red, this thing? So that means there is an outlier in cap. Both, we have used two methods so far to test for outlier using what? Grubs and box plot. So now let me state something. There are sometimes that both of them may not agree. Both of them may not agree. So in such situation, what do? You can decide to use a third method to know a third method for testing outlier. You can decide. This when you're doing analysis, you are free to do some things as far as you have not done anything against statistics. So you can decide to use a third method. Then after using the third method agrees with the grubs method, you go with it. Third method agrees with the box plot, you go with it. Or you can decide to go online, check for the one that is more powerful. If the grubs and the box plot are not saying the same thing, you now check, is the grubs more powerful than the box plot? So you can go online and confirm from researches of fellow statisticians. They will tell you the one that is more powerful. Then you go with the result of the one that is more powerful. But in this particular data, both of them are saying the same thing. What are they saying? They are saying that grubs cap has an outlier, while the other variable doesn't have an outlier. And box plot was able to tell us the exact value that has an outlier. Box plot told us is this value that is an outlier. This value is a strange number. Outlier means extreme values. Others are, that means you are totally different from what others are getting. So that's the meaning of outlier. So it has failed one assumption. You can't continue. You can't continue. Once it has failed an assumption, you can't continue. You have to look for a solution. Now, one of the solutions is to delete this case. You cannot delete this, because if you delete it, since this is where the outlier is, you can decide to delete this. and repeat the analysis from the beginning. That's how I'm looking for a way to solve the problem. So I can use this to solve the problem. So for this class, I'm not teaching Malanobis distance. If you want to learn it, you can learn it yourself. But we are teaching box plot and growth methods. So using box plot and growth test for outliers. So we're using box plot and then growth method to test for outliers, not Malanobis distance. So I've shown you how to solve the problem of, there are some you cannot use. If you can solve the problem of the failure of the assumption, awesome. But if you cannot solve the problem, you look for another method to use. So for the outlier, I just deleted that case. So I deleted that case, I have to repeat the analysis now. Regression, linear. So you repeat the analysis. That's it. Repeating the analysis, like there will be a problem. This data I'm using, they're not giving me what I want. Okay. So let me test again if there is an outlier. So let me check for cap now. After deleting the case, there's still an outlier, 15. That's one of the problems we encounter in data analysis. What's the problem? When your data, you want to use a particular method, your data doesn't satisfy the assumption. If you force the method on that data, you are doing something wrong. You are committing a crime in statistics. You don't force a data to suit a method, or you don't force a method to suit a data, to suit data sets. You don't force it, it's wrong. So you look for another method to use, another method to use, another method to use. So now let's assume that all the assumptions are satisfied. So the main thing I want to teach is how to interpret regression. So let's just assume all the assumptions are satisfied. All the assumptions are satisfied. Let's assume they are satisfied. So how do we interpret regression? Because I can't continue looking for another data set. So normally it's satisfied. In this case now, the only assumption that failed is an outlier, but the others are satisfied. So remember I told you, even if it has, as far as it has failed one, you can't continue. So almost scalasticity was also satisfied. For almost scalasticity, there must not be a pattern. Then let me just explain for what I mean by a pattern. Look at my cursor now. When something is moving like this, there's a pattern. That means you can trace the line. If it's moving like this, you can trace the line. It means there's a pattern. If it's moving like this, you can trace the line. But in this case, you can't tell me the line is going. Everything is scattered. So because it is scattered, you say there is no what? There is homoscedasticity. Underneath for this is there is constant variance. Underneath for it is there is no heteroscedasticity. So now this is what I want to teach today. This is what I want to teach. Then maybe we'll end here for today. Then continue tomorrow. So we'll end there for today. So what do we interpret? The first thing you interpret in regression, after the data are satisfied all the assumptions of OLX. So what do you interpret? We interpret R square. We interpret R square. The first thing. We interpret the test for the significance of the model. The second thing. Then we interpret test for the significance of the regression coefficient. The third thing. Before you can now write the model and interpret each of the variables. Very simple. So let's start from the first thing you are supposed to interpret. We interpret R square. So what's R square? R square is also called coefficient of determination. R square is also called coefficient of determination. So what does it mean? It tells us the percentage of variation in the dependent variable that can be explained by your model. So now let me explain it in simpler terms. Now remember, regression is about studying the relationship between the dependent and one or more independent variables. For example, I'm using the number of hours a student spend reading to know the score the student will get in my course. That's a regression analysis. So I can also use two variables, the number of hours the student spend reading, and also where the student residence of the student, where the student is staying. So I want to use both of them to be able to predict the score of the student in the course. So that's a regression analysis. Now, if at the end of the day, I discover that there's another variable that explains, that influences the score of the students, and I've not included it in the model, it will affect their root square. That is good. Oyemachi, are you seeing my screen? Oyemachi? Emmanuel,
Yes,
are you
yes,
seeing my screen?
yes,
You are seeing my screen, right?
yes.
Okay, Santos, please, is your network. Let me stop sharing and share again.
Okay, sir.
Are you seeing, Santos, are you seeing where I am now? So I said, I'm trying to use an example so that we
I'm not
understand.
seeing it. I'm seeing it now.
Okay. So I'm trying to use an example to explain a root square. So I said, I want to study relationship between the score of a student in a course, and I want to look at the variables I want to use to understand this. One, I'm using the number of hours students spend reading and the residence of the students. Now, assuming there's another variable that is even more important than these two variables that influences the score of a student. Like what this variable can be, who the student sit close to in the exam hall. So that's the third variable. Who the student sit with in the exam hall, or the score of the, let me just put who the student sit with in the exam hall. Is the student sitting close to the best 10 students or the last 10 students? Like when talk about the CGPA. So if I'm considering the third variable, and the third variable is who the student sits close to in the exam hall. Now, this third variable may have more influence to the student exam score than the first two that I've been mentioning. But when I did the regression, I didn't consider who the student sat close to. So because I didn't consider it, this my arrow score will be low. Why will it be low? It's trying to tell me that the model cannot explain all the variation that happened in the student exam score. It's trying to tell us that there are some variation that are yet to be explained. And the reason why they are yet to be explained, one of the reasons can be there are some variables that are still missing in your model. So you have to look for a way to consider those variables and put them in your model so that more variations can be explained. So arrow square it tells us your model, how many percentage of the percentage variation that it can explain. So if the percentage variation it can explain is low, it means you have to look for a way to increase it. And one of the ways we can increase it, we can look for variables that we know that can influence the dependent variable and include it to the model. So that's arrow square. So this is the first thing. We want it to be very high. It's between 0 and 1. Then you must convert it to percentage. So the arrow square value is what? 0.965. And it tells us that the model can explain 96.5 variation in the dependent variable. So that means this model, now what is this arrow square is an inbuilt mechanism to tell us the goodness of fit of the model, how fit your model is. I said what is an inbuilt mechanism that tells us how fit a model is. It's an inbuilt mechanism that tells us how fit a model, how fit, how good a model is. So in this case, the model is okay. The second thing that is very important is the significance of the model. How do you test the significance of the model? This is what you use. This is what you use. This ANOVA, the ANOVA in regression. ANOVA in regression. That's what you use to test the significance of the model. The ANOVA in regression is what you use to test for the significance of the model. Now, the null hypothesis is that the model is not significant. When we say the model is not significant, it means they are nonsense. They can't predict the dependent variable. They don't affect the dependent variable. So based on this example I've used, it means the number of hours the student spend reading, whether the student hours or the student spend a few hours, it won't affect the exam score. Whether the student is staying in the hostel or is staying Umishima or staying at Zobodo, staying at Yagua, it won't affect the score. So that's the meaning of this. It's trying to tell us that all the variables that we are using to predict exam score, they are nonsense. They are insignificant. Insignificant means they don't have any effect. So that's what we are testing. So we want to check all these variables we are using, are they really significant? Should I continue using them or not? Or should I just drop all of them? So that's the meaning of this ANOVA test. So we call it what significance of the model. So I remember I told you can write it this way or write it in words. If you want to write it in words, so we are going to test for the significance of the model using the F statistics from the ANOVA table. The hypothesis for this test are, or the null hypothesis for this test is that the regression coefficient or the model is not significant. And this is tested against the alternative hypothesis that the model is significant. Another way of saying the model is significant is that all the regression coefficients are significant. Take note. I take note of that keyword, all. So, and this will be tested at alpha 0.10. Then the null hypothesis will be rejected when the p-value is less than the level of significance. So in this case, we are going to reject, and we are rejecting, and we are saying that what the model is, because we are rejecting this, we are rejecting H naught, means we are going with this, that the model is significant. So if you watch where arrow square has told us that the model is good. Remember, I say it's an internal mechanism to check how good the model is. So it's telling us that the model is good because it's high. The test for the significance of the model has also told us that the model is significant. That means the model is also good. So both of them is trying to, they're almost saying the same thing. Now, yes, you can go on with your model. Your model is saying your model is powerful. Then the third thing is, now the difference between this second test and the third test is that this second test just told us that the model is good. But let me use an example of a class. Or, let me use a football team. A football team can win the Champions League, and you say, wow, they have a good team. They have standard players. They have world-class players. But you know that it's possible that even though they have world-class players, there's a player there in that team that is very poor, that's not world-class, that is even below, that is a poor player, is not a good player. Now, even though they won the World Cup or they won the Champions League, and people are generalizing that they have a world-class team, they can generalize because why? Most of the players are very good. So it's as if the few that are not good will not really be significant. So now back to this. The ANOVA will just tell us that the model is good. But it's possible that even though the model is good, one or two of the variables that make up the model may not be okay. Like I've tried to explain. You have a team. You can say all the players are good because they won Champions League. But it's still possible that one player is not performing very well. So that's what I'm trying to say. The model will just tell us this second test will tell us that the model is good, but it will not tell us the exact variables that are not good. So I can teach a class. I discovered that the 98 or 70% of the class failed my course. I will just come to the class and say, you guys failed my exam. If that's a generalization, I just made a general statement that you guys failed my exam. Why is it that? Why did I make that statement? Because 70% failed my exam. But it's still possible that in that class, someone will still get A in my course. But that's what the third test will do. The third test now will now pick each of them to check them specifically. Are you good? If you are good, it will mark correct. Then it will go to the second one. Are you good? So that's what the second test is doing. That's what the third test is. The second test is just giving us a general statement. Then why this other test for the significance of each of the regression coefficients. It will test each of the regression coefficients. So in this case, we have two regression variables. We have cap and we have rec. So it will test rec. It will test cap. So looking at this one, because I'm using alpha 0.10, it's telling me that cap is okay. And also rec is okay. That means at 0.10. But if I'm using 0.05, cap will no longer be okay. That means it's only rec that will be okay. So this thing will also tell you the variable that is adding more. So based on this, rec is contributing more to explain the dependent variable than cap. So this test is also interpreted the same way as this, but the difference is that now we are considering each of the variables. So interpret each of the, so look at the interpretation. We reject the null hypothesis for cap since the p-value is this, and we say cap is what? Significant. We also reject the null hypothesis for rec since the p-value is this, and conclude that. So what this third test is doing is that it will analyze each of the variables and make conclusion on each of the variables. So that's what this test is doing. Then the last thing is you now write your regression model. You write your regression model. You write your regression model. How do you write a regression model? You put the dependent variable first, which is GDP. So this, let me write my regression model. Listen to me clearly. So GDP equal to, you write this value. Then the next thing is, since here it's minus, it now be minus, you write all this value, minus 16.001 times cap. When you are done with this, because this is plus, you now put plus 27.048 times rec. So that's what we have here. Are you seeing it? So you be the this one arrow will not SPSS will not give you be the one to write it. So the last thing is you have to explain this model that you've written. Remember, we got the model from this. So let me say it again. GDP equal to, you write this, minus 16.001 times cap plus 27.048 times rec. Here is minus because of here is minus. Yeah, rec is plus because here is plus. So now how do we interpret the model? And that's the last thing you interpret. The first thing you interpret is what? Arrow square. Second thing, the significance of the model using the ANOVA table. Third thing, the significance of each of the regression coefficients. Then the last thing is the fourth thing is to write your model. The fifth thing is to explain the values in your model. Now, the first value is called the intercept, or is called the constant. This first value, 1 minus 1.2, is called intercept of constant. So how do you interpret it? You interpret this value as the value of GDP. So look at how I'm interpreting now. So the value of GDP when cap is 0 and when rec is 0 is, that's it. That's how to interpret it. The value of GDP when cap is 0 when rec, remember cap is my dependent variable. It's my independent variable. So the value of GDP when cap is 0 and when rec is also 0 is minus 1220.67. Very simple. So let's look at how I interpreted it here. The capital expenditure negative. Okay, no. That I've explained this constant. So now let me explain this minus 16.001. Let me explain minus. How do you interpret? How do you explain this? To explain this, you look at the sign. Is it plus or minus? When it is plus, we say there is a positive relationship. When it is minus, we say there is a negative relationship. So in this case, it is minus. So listen carefully, listen attentively how I want to interpret it. Because it's negative, I would say GDP and cap have a negative relationship. So I will write for 1 unit increase in cap, increase in cap, GDP will decrease by 16.001 units. For 1 unit, so if you cap increase by 1, GDP will decrease by minus. We double minus again because that decrease has taken place of the minus. So let me start all over. For cap, there's a negative relationship between GDP and cap. This means that for every 1 unit increase in cap, 1 unit increase in cap, GDP will decrease by 16.001. Similarly, let me interpret for rec. Because rec is plus. Plus means in positive increase. It's not decreasing, it's increasing. So I will interpret rec now. So there's a positive relationship between GDP and rec. This means that for 1 unit increase in rec, the GDP increases by 27.048. Then you must put this statement that given that all the other constant are all the other coefficients are held constant, very important. Given that all the other coefficients are held constant, very important. So that's it. Very simple. Santos, any question? Now, Santos, do you have any question?
No, sir. No, sir.
The only way you will know if you understood what I explained is when you do it yourself. You have to do it yourself. And when you do it yourself, you know whether you've understood. Like, look at what this people submitted, I was happy. Look at the assignment. It shows that they've understood these parts. They've practiced, and it shows that they've understood. They were able to tell me that there is an outlier here. They were able to tell me there is an outlier here. They also told me there is auto correlation. Like, yes, it means that they understood what I thought. So you have to do work on this yourself, then you know whether you've understood it or not. So we are done with regression. Now, I said we have simple regression and multiple linear regression. Both of them are done the same way. What's the difference? In simple regression, we only have one independent variable. For multiple regression, we have two or more independent variables. Now, if you're working with simple linear regression, you don't need to test for multicollinearity. Why? Because multicollinearity is tested when you have more than one independent variable. So if you are doing a simple linear regression, you do every other test except multicollinearity test. I think we are going to stop here for today. Any question? No question, right?
Yes,
The next we are supposed to learn is okay. Let's see if we can ANOVA. Okay, let's try ANOVA. Okay, we have this 445. Okay, let's try. Okay, Masha, are you still with us?
Yes.
Okay, let's just use 30 minutes to learn or 15 minutes to explain ANOVA. Then we will stop. So when we talk about ANOVA, we're talking now for we've learned t-test. T-test can only work for one sample or two samples, one population or two populations. Now, in a case when you have three populations, you can't use t-test. So what do you use? ANOVA. So it's still the same definition with t-test. It's used for comparison. That's what it's used for comparison. To test if there is a significant difference among three groups. So example, if we have two vaccines already in existence, or let me say we have two companies producing bulbs. Company A, owned by Santos, is producing bulb A. Company B, owned by Emmanuel, is producing bulb B. Then I want to start producing a new bulb. I want to create my own company, Company C. So I need my company to be performing better than Company A and Company B. So I will now, after doing everything, I have to carry out my ANOVA test to check if there is any significant difference between the three products. That's what we mean by ANOVA, trying to compare. It must not be three, it can be more than three, but just know it's more than two. Whenever you are doing ANOVA and you have only two groups, the answer will be the same as t-test. But when you have more than, remember, t-test can still do for two groups, so the answer will be similar. The conclusion will be similar. So we use ANOVA for two. You can still use it for two groups. That's what I'm trying to tell you. So two or more groups. But when you use it for two groups, the answer is similar to t-test. So it's used to test for significant difference between two or more groups. I think we can stop here for today. Let's stop here. So I've defined what ANOVA is. Then we'll continue tomorrow. So I can stop my recording now.